Okay, so here we have an equation where the x is right up here as an exponent, and you're solving for that. So where you want to get to is an equation where you have the base and that exponent alone on one side of the equation and stuff on the other side of the equation. Something that evaluates as to numbers. Then you take the log of both sides. Log of a number is a number, this cloud of numbers. And when you do that, you can use that power rule and bring that exponent, which is x, off to the side. Then solving for x means divide both sides by that. Okay? So let's try this. Let's subtract 350 from both sides. It's going to be 1,000. And then we're going to divide both sides by 660. And 1,000 divided by 660 is this giant number here, 1.51511515. But I'm going to just leave it as a fraction for now. I'm just going to call it 1,000 over 660. But I've canceled these, so I have 1.075 to the x. Here's where I do my log move. Take the log of this side and the log of this side. And then final power move. X goes down here. X log of 1.075 equals log of this piece right here. Okay, final move. Divide both sides by this. Blam, those are gone. Here's my answer. X equals this thing right here. So if I go back to my calculator, I can do it all in one step. Log of this thing, whole thing divided by log of 1.075 is 5.745. And they wanted it to the nearest tenth. So here's my tenth, 7. Oh, keep it 7. Okay. Now, how do we solve something when you have a log or the variables inside of the log, and you have two logs? Okay. What you want to get to is a single log. Log base 3 of something equals a constant. And you can see that constant is 1. That's where you want to get to. So how do we accomplish that? Well, we know about condensing logs. It's the opposite of expanding logs, but condensing logs, and since they have the same base, you can do that. You follow this rule. A plus log of B is log of AB. And then once you've done that, you're going to rewrite this equation as an exponential statement. And that means you take this as your base and you say, what is a log? It's an exponent. So whatever ends up over here is your exponent, constant, equals, this is the value of the log. So it's going to be a rewrite, okay? But first, let's condense these logs and get to this stage right here. Okay, let's condense. We got a single log base 3 of these two things being multiplied. Now make sure you keep these two things separated. Here's one and here's the other. Okay, no need to distribute quite yet. I think we will distribute, but so this is now been condensed into a single log. Okay, so actually, let's go ahead and distribute. Let's rewrite this as x squared minus 2x equals 1. Okay, now we're going to write this as an exponential statement. We're going to pick apart the three pieces. This is the base. This is the exponent. These two things are the same thing. The log and the exponent are 1. That's a coincidence. Equals, this is the result, x squared minus 2x. Oh, sorry. Okay, so this is your standard quadratic equation, right? If you're trying to solve for x, but you have an x squared in your equation, you know you have to have a different kind of strategy. And that strategy is the zero product property, meaning we've got to make one side of the zero, we've got to factor the other side, and those factors will tell us the two potential solutions. Okay, so let's switch sides. I'm going to say x squared minus 2x, and I'm going to take 3 away from both sides. Minus 3 equals 0. So that's part of 0. I've just kind of switched the sides of the equation, okay? And this is a pretty tame x method solve. I think it must be -3, +1. And there's nothing here, so I can just go ahead and plop those values into my equation. Equals 0. Okay, zero product property means when you set up a product, right, and you know it equals 0, the solutions are setting these factors to 0. These, I'm going to say, these are potential solutions. Why do I say that? Because you have to put them back into the original equation and make sure you don't have any problems. Because if you do, then one or both of these will be extraneous. Now, when would you have a problem? A little side comment. You cannot have a log of a 0 or of any negative number such as -1, because mathematically there is no way. Let's pick a base of 2. Doesn't matter what the base is. You cannot take 2 to any power and come out with a 0. You just can't. 2 to what power? I challenge you. To what power will you result in 0? Now, that's totally different from saying 2 to the 0 power is 1. Guess what? Log base 2 of 1 is 0, because 2 to the 0 power is 1. But when you switch them around, that's an impossibility. Nor can you take any base, and bases are always positive, to any exponent and end up with a negative number. You just can't do it. So look out for zeros inside a log or negatives inside a log. Okay, 3, not a problem. 3 minus 2, oops, not a problem. Good. -1, that's a problem. This is an extraneous solution. So the only solution to this equation is x equals 3. What if you have a problem like this? 2 logs. This happens to be natural log on both sides, one on each side. Okay, this is fairly straightforward because log of one side, log of the other side. That means the insides are equivalent. Okay? And once again, you've got yourself a quadratic equation, which means your strategy is just like the one before, x squared. And let's subtract this x from both sides. Minus x minus 2 equals nothing. Okay, this is what you're working with. So, same idea. You're going to factor this. It's factorable. You're going to pull the solutions from these factors, but you're going to test these solutions. You're going to test these solutions by plugging them in to both and making sure you do not get a situation where the solution, well, where the inside of the log is less than or equal to 0. Sorry, you should be plugging it into the x, which gets squared. Okay? This means that solution's extraneous. Now, how about this monstrosity? Before you start freaking out, just take note of the structure of this equation. The structure is that you've got x in the exponent position, but you have two of them. You have an x here and you have an x here. This, as you can see, is called a common base equation, where you're going to set up, kind of like the one we just did, an equivalency on both sides. What you want to get to is, I'm going to make up a very simple example, is something like, 5 to the x plus 2. And here's that base again, 5 to the 2x minus 1. I just made something up. This is what you want to get to, because when the bases are common, you can ignore them, you can cancel them, and then just work with the exponents themselves and make them equivalent to each other and solve. Okay? And this is solvable. But so is this, as crazy as this sounds. Now, look, as crazy as it looks, look at that base and look at this base. They are clearly not common the way they look right now. But we can play a trick and make them common. A simpler example would be this. If you had maybe 3 to x plus 1. On the other side, you've got 9 to the x minus 3. Okay? Two bases, not common. But guess what? 9 is 3 to the 2 power, isn't it? So when I replace the 9 with 3 to the 2 power, this power and that power are both in the power position. And so they multiply to each other. Just as you learned that rule, a to the b to the c is a to the bc. Two exponents that are next to each other, they multiplied. Okay? Just like they multiply here. So that way, in this simple problem, you can make x plus 1 equivalent to this, and then solve for x. Well, we're going to do the same thing down here. Okay, this is crazy. The one twist here is 4096 is in the denominator of a fraction. Okay, all that means is when we find the base that's common between them, this one will have a negative exponent. Negative exponent. Because negative exponents push things into the denominator. Okay. So 4096, there's a base and there's an exponent that'll get you to that. And it's just got to be negative after you've done it. So let's explore. And it makes sense to explore with the smaller of the two. I mean, this is just an insane number you've never seen before. But let's play with 4096. Is that a power of some base? And just here's a little advice. You know, the bases are not going to be really big numbers. A lot of them, I think most of them are less than 10. So start with a base, seems reasonable. Powers just make numbers explode. So you'll be, you or not, you may be surprised at how big numbers can get with a simple power. Like I'm just guessing 4. I seriously don't know. 4 to the 4? Okay, that's big, but not big enough. 4 to the 5? How about 4 to the 6? Now, honestly, that was a total guess. 4 to the 6 makes 4096. Okay, so 4 to the 6, that is going to be 4, not to the 6, because that's 4096, 4 to the negative 6. And then here's the rest of the exponent, negative 2x plus 7. Okay, now that I have 1, I know the way these problems are set up. 4 is the base of this. There's some exponent that's going to take you there. Okay, so you just have to play with it. Whoops. 4 to the, let's see, how about 9? Overflow. Oh, no, I didn't do 9. 9. It's too big. 8. Okay, 7. 8. 9. How many digits does it have? 8. 7. Between 16,000 and 65,000, I'm missing it. So it's not 4. I was fooled. Is it possibly a 2? Should I go down? Okay. 2, let's say, to the 12. Okay. It's not, sorry, the base is not 2. The base is not 4. I can get there by doubling the exponent and shrinking my base by 2. So 2 to the 12. So I just fix it. So it's 2 to the 12, not 2 to the 12, 2 to the negative 12, because I want to make it into a fraction. Okay, so 2 to the what gets me this? Okay. I don't know, 13, 14, not 114, 14, 15, 15, 15, there it is, 32,768. 2 to the 15. But it's 2 to the 15, and here's the other exponent right next to it, 5x minus 11. Okay? So the equivalency is now complete. Next step is to set this equal to this. And of course, you're going to distribute that 15 to both, distribute that negative 12, and then it becomes linear algebra, because all you have is a plain old x, not messing with x squareds. And you bring the x's to one side, bring the numbers to the other, you have your answer. So I put in my answer, I put in a blank answer just because I wanted to see how Delta Math does it. And you know what? What the common base is, the bigger, it's 8. So 8 is the common base, but so is 2. Honestly, it'll work either way. As long as you're able to come up with a common base and the powers that you choose for each of those values gets you to the number that you want, it will work. And so I didn't think to go up higher from 4 to 8. I went down instead to be on the safe side. But trust me, it will work as long as you have the common base. This is interesting to know that numbers can have different bases, and of course the exponents will be different depending on the size of the base.